Welcome to the lecture series on numerical methods. Last class we have discussed this numerical integration based on trapezoidal rule, composite trapezoidal rule and Simpson's rule. So today we will just go for the discussion of this integration method based on composite Simpson's 1/3 rule and some of the examples based on composite Simpson's 1/3 rule and then Simpson's 3/8 rule, and then we will just go for some examples of 3/8 Simpson's rule. So last class we have discussed about this 1/3 Simpson's rule. There itself I have just written this formula, this 1/3 Simpson's rule as integration a to b f of x dx. This can be written in the form of like h/3 f of a plus 4 f of a plus b by 2 plus f of b, where h can be defined as b minus a by 2 here. Since we are just dividing this total domain into two subparts here, if our starting point is a equals to x0 here, then middle point we are just assuming that a plus b by 2 here and the last point b as x2 here. So middle point is x1. Then we can just rewrite this formula as in the form of like h/3 f of x0 plus 4 f of x1 plus f of x2 here. So if you just go for a composite formula of this 1/3 Simpson's rule, then since we are just considering only two sub intervals here, then the total intervals should be divided into 2n plus 1 number of nodal points. Then we can just use the Simpson's 1/3 rule there. And if you will just go for the step size here, then for composite Simpson's rule here, composite 1/3 Simpson's rule, we have to divide this total interval that b minus a by n sub intervals here. This means that this is a 2n we have to consider, since total number of tabular points is 2n plus 1. And the nodal points, it can be chosen either in the form of like a equals to x0, then x1, then x2. Since all are of equispaced here, then we can just write x3. So likewise we can just write the last point here, that is in the form of like x0 plus 2nh, that is xn here, this equals to b here. So that's why it is just considered it of like 2n plus 1 points here. So that's why we can just consider a equals to x0, then x1 equals to a plus h or x0 plus h, then x2 equals to x0 plus 2h. So likewise just we can just write the last point, it can be written in the form of x of 2n. If you will just write, since 2n plus 1 points here, so if you will just write x of 2n, so then it can be written as x0 plus 2nh here. This equals to b here. So if we will just write this 1/3 Simpson's rule in a composite form, then we can just write this integration that as in the form of a to b f of x dx. Since we are just starting this point from x0 here, so x0 to x2 f of x dx plus x2 to x4 f of x dx, plus likewise we can just write the last point as x of 2n minus 1 x of 2n f of x dx here. Sorry, we have to write this one as x of 2n minus 2, since twice points it is just required there, that is one sub interval, since we are just dividing. If this point is written from x0 to xn here, then xn can be replaced as 2n here, then equally we are just subdividing this domain into 2n parts there. So that is why we can just write, since the starting point is x0 to x2 here, then x2 to x4. So last point it will go from x of 2n minus 2 to x of 2n here. And in each of the intervals, if you will just use this 1 by 3 Simpsons rule, then specially it is called Composite Simpsons rule here. So then if you will just apply this 1 by 3 Simpsons rule in each of these intervals here, then this formula can be written as, in the first interval x0 to x2 f of x dx, this can be written as like h by 3 f of x0 4 f of x1 plus f of x2 here. Similarly, in the second interval, if you just write x2 to x4 f of x dx, this can be written as h by 3 f of x2 4 f of x3 plus f of x4 here. So likewise, if you will just write the last interval, it can be written in the form of x of 2n minus 2 x of 2n f of x dx here. This can be written as h by 3 f of x of 2n minus 2 plus 4 f of x of 2n minus 1 plus f of x of 2n here. So if you will just add all these terms, then we can just obtain this composite trapezoidal rule, that is in the form of like integration a to b f of x dx, this equals to h by 3 f of first point, that is x naught, plus last point f of x2n plus the 4 coefficient terms, that is f of x1, f of x3 up to f of x2n minus 1 here. So that can be written as like f of x1 plus f of x3, so up to f of x of 2n minus 1 plus twice of the repeated terms. If you will just see here, like f of x2 is appearing here, f of x2 is appearing here. So then again f of x4 will appear here, then f of x4 is appearing here. So that is why we can just write twice of this even number terms, that is f of x2 plus f of x4 plus up to f of x of 2n minus 2. So this is basically called the composite 1 by 3 Simpsons formula here. And if you will just go for this error computation of this 1 by 3 Simpsons rule here, then last class we have just derived this error for this Simpsons 1 by 3 rule. And if you will just consider like our earlier trapezoidal rule, so in each of these intervals we will have a maximized error, that is in the form of like minus h by 90. So first error, if you will just see for this interval here, that is minus h to the power 5 by 90 f fourth of zeta 1. Second one, if you will just consider here, that is h to the power 5 by 90 f to the power 4 of zeta 2 here. So likewise, if you in each of these intervals, if you will just take these error terms and if you will just add all these error terms, then we can just get this one as in the form of like minus h by h to the power 5 by 90 f to the power 4 of zeta 1 plus f to the power 4 of zeta 2 up to f to the power 4 of zeta n. Since we are just dividing this 2n number of points or 2n plus 1 number of points into 2n number of intervals here, and then in twice of this interval or sub intervals, like 2 points, within 2 points we are just getting one error term. So that is why this total number of error terms, it will be like n number of terms there. So that is why the last point of this error term, it is just coming as f to the power 4 of zeta n here. And in a composite form, if you will just write, that is the maximum bound of error, that is the absolute modulus of r of f of x. If you will just write here, maximum modulus, that is r of f of x here. So we can just write this should be less or equal to first term here, that is h to the power 5 by 90, and if you will just consider all other terms, f to the power 4 of zeta 1, f to the power 4 of zeta 2, plus of 2 f to the power 4 of zeta n here. Or we can just write this way, n as like 2n by 2. So that's why if you will just consider all these terms at a time, so it can be written in the form of like this should be less or equal to h to the power or n h to the power 5 by 90. So this can be written as n h to the power 5 by 90, and this maximum error that is occurring between a to b for this f4 of x here. This one we can just write maximum of f to the power 4 of x, where x should be lies between a to b, this one. And obviously sometimes we can just write that one nh equals to b minus a by 2. If you will just see here, that is your h size that is defined as b minus a by 2n here. So nh, if you will just replace here like nh, this equals to b minus a by 2. So we can just write this one as like h to the power 4 by 180, and b minus a, maximum of x lies between a to b, f to the power 4 of x here. So this one is the representation of error in composite Simpsons 1 by 3 rule here, and it can be observed from the expression of error that this composite 1 by 3 Simpsons rule is of order 3 here. Since fourth order term, it is just giving the error term here. So since we have already explained that one, usually if this error term is written in the form of like integration a to b f of x dx minus summation k equals to 0 to n lambda k f of x k, this equals to c by p plus 1 factorial into f to the power p plus 1 zeta there. So that's why p should be the order of this polynomial which will give you the exact solution. So that's why for degree 3 we are just exactly getting 0 values at this integration level. So that's why this order of this error terms can be considered as 3 here, since p plus 1 equals to 4 here. So next we will just go for the example of this 1 by 3 Simpsons rule, and this composite 1 by 3 Simpsons rule here. So if you just go for this Simpsons 1 by 3 rule, then suppose the example is given as like find the approximate value of this integration, that is I equals to integration 0 to 1 dx by 1 plus x using Simpsons 1 by 3 rule with 8 equal subintervals. 1 by 3 Simpsons rule for 8 subintervals. So if you just use this 8 subintervals here, then we can just consider that n equals to 2n, that equals to 8 here, and then we can just define this h, that in the form of like b minus a by 2n here, and then we can just write this one as 1 by 8 obviously, since your integration range a is given as 0 here, b as 1, so that's why it can be written as 1 minus 0 by 8, that as 1 by 8. And the nodal points, if you will just write in this form here, then it can be written in the form of like x0 equals to 0, x1 equals to 1 by 8 means 0.125, x2 equals to like 0.25, x3 equals to 0.375, x4 equals to 0.5, then x5 this equals to 0.625, x6 equals to 0.75, x7 equals to 0.875, x8 equals to 1.0. And then if you just use this following tabular values for this function, f of x equals to 1 by x here, 1 by 1 plus x, then this functional values that will just give like the values as 1.0 for 0 here, since if you will just see x equals to 0 means this is f of x equals to 1, then 0.125 it will just give you 0.88889, then 0.25 it will just give you 0.8 here, 0.375 this will just give you 0.727273, 0.5 it will just give you 0.6667 here, 0.625 this value will just give as 0.615385, 0.75 the value will just give as 0.571429, 0.875 this is given as 0.533333, and 1.0 obviously it is 1 by 1 plus 1, so that is why it will just give you 1 by 2 means 0.5 here. So if you just use this formula here, then this integration can be written in the form of like h by 3 f of x0 plus f of xn, that is like 1.0 here, plus 4 times the even terms here, that is in the form of like if you just write x1 plus f of x3 f of x5 odd terms here, sorry, and then last point is f of x7 here, then plus 2 into f of x2 plus f of x4 plus f of x6 . So if you just put all these values here, the corresponding nodal points whatever it is just defined, so correspondingly this functional values if you just put in this formulation here, then you can just obtain this value as 0.10615 here. And if you just see this exact value, so this value is just giving you like 0.10615 here. And if you will just see I exact value, so this is nothing but 0 to 1 dx by 1 plus x here, so it can be represented in the form of ln of 1 plus x, this is 0 to 1 here, and this is nothing but ln of 2, this one, since ln of 1 is 0, and this value is coming as 0.693147. And first value if you will just see this one, so this integral value just coming as like so this value is coming as like 0.693155 here, and if you will just take the difference of I exact minus IAS here, then we can just obtain this value as 0.693147 minus 0.693155 here, so this will just give you like 0.00008. So error is very less here for this case. So next we will just go for Simpson's 3 by 8 rule here. In this method, so f of x is approximated by a cubic polynomial, since in the beginning of the first case, that is trapezoidal rule, we have written that f of x is approximated with a linear polynomial. Then in the second case, like 1 by 3 Simpson's rule, we have just taken that f of x is approximated by a quadratic polynomial. Then for Simpson's 3/8 rule, we will just consider that f of x will be approximated by a cubic polynomial here. To construct this cubic polynomial, so 4 nodal points are required at best, we can just say like x0, x1, x2 and x3 here. Hence, this interval will be subdivided into 3 equal parts to obtain 4 nodal points. So, for that we have to consider h equals to b minus a by 3 there, and the nodal points can be written as, nodal points are like x0 equals to a, then x0 plus h equals to x1, x0 plus 2h as x2 here, then x0 plus 3h, this equals to x3 here. So, usually we are just defining these sub intervals, 3 sub intervals. So, that is why we can just write this one, a equals to x0, 1, 2, then 3 sub intervals, x1, x2, x3 here, h here. Now, if you will just go for this Newton's forward difference formula like the earlier cases. So, the cubic polynomial approximation for f of x, interpolating these points like p of x0 f of x0, then q of x1 f of x1, then r of x2 f of x2 and s of x3 f of x3, then we can just write this formula that is in the form of like f of x0. If you will just write these 3 different terms like f of x equals to f of x0, so first term can be written as x minus x0, so p delta of f of x0 plus x minus x0, sorry, by h it will be there, x minus x1 by h, 1 by 2 factorial del square of f of x0 plus x minus x0 by h, x minus x1 by h, x minus x2 by h, 1 by 3 factorial delta q of f of x0. Then we can just obtain this formula for this 3/8 Simpson's rule here. So, just then we will just take this integration here, that is in the range of from a to b here, a to b, then a to b, dx here, integration x0 to x3, or you can just write a to b, dx here, then a to b, dx here. If you will just integrate this one, then you can just obtain this formula that is in the form of like 3h by 8 f of x0 plus 3 into f of x1 plus 3 into f of x2 plus f of x3 here. So, this expression is basically called the 3/8 Simpson's rule here. So, all of these values it can be expressed in the form terms of x0 and h, since x1 can be written in the form of like x0 plus h, x2 can be written in the form of x0 plus 2h and x3 can be written in the form of x0 plus 3h here. And the error approximation for this Simpson's 3/8 rule, if you will just go like our earlier computation, then we can just obtain this one as r of f of x here. This equals to minus of b minus a whole to the power 5 by 28, sorry, this is 6480 f to the power 4 of zeta here, where zeta should be lies between a and b. And in terms of h, if you will just write, this can be written in the form of like a minus 3 h to the power 5 by 80 f to the power 4 of zeta here, and h can be written in the form of like b minus a by 3 here. And from this expression it is also shown that this order of approximation for the error is a third order here also, since when f of x is a polynomial of a degree less or equal to 3, then R3 of f of x it is just giving the 0 value here. And this shows that the error increases as b minus a values are increasing here also, and in this case this interval ab is subdivided into a number of subintervals that can be represented in terms of 3k plus 1 here. So, earlier it was 2n plus 1, since 2 subintervals we have just considered. So, here 3 subintervals, so that is why it can be considered as a 3k plus 1, total number of points small n equals to 3k plus 1 here. Then simply we can just use 3 by 8 Simpson's rule. Then if you just go for composite Simpson's rule here, then the total number of points can be taken as 3k plus 1, where your h can be divided in the form of like b minus a divided by 3k, or we can just consider this 3k equals to n is the total number of points there. And all of these nodal points, it can be represented in the form of a equals to x0, then b equals to x0 plus 3kh, that is xn, usually it can be written. So, if you just write here x0 equals to a, then x of 3k, this can be written as xn equals to b here, and usually it can be represented in the form of x0 plus 3kh, the last point. And in composite form, if you just write this 3 by 8 Simpson's rule, then it can be written in the form as integration a to b f of x dx, this equals to, this is composite 3 by 8 rule. Especially it can be written in the form of like 3h by 8. So, first point f of x0 plus f of xn is the last point, plus 3 into f of x1, f of x2. If you will just see here, so 2 coefficients, that is x1 and x2 takes the 3 coefficients, and the last point f of x3 is considered as the single coefficient. Again, if you will just apply this one, the starting point will be f of x3 there. So, that is why these points will goes up to f of x of n minus 1 points. So, plus 2 into f of x3 plus f of x6. So, likewise it will just go up to f of x n minus 3 here. This is basically called composite Simpson's 3 by 8 rule. Similarly, the error can be computed by considering, since we are just considering this 3 subintervals at a time. So, that is why it can be divided by 3, means we can just finally consider as k intervals here, or k maximized values within this subintervals. So, that is why this final error term can be written in the form of 3 by 90 k h to the power 5, maximum of f to the power 4x, x lies between a and b here. So, using this 3 by 8 rule, if you will just try to solve one problem, basically the problem statement, it can be written in the form of like suppose I equals to 1 to 2 dx by 5 plus 3x with 3 and 6 subintervals. Then we can just define this problem as, the given problem states that I equals to 1 to 2 dx by 5 plus 3x here, and we have to consider 3 and 6 subintervals. So, here we can just consider n equals to 3 first, then n equals to 6 here. So, a equals to 1 here, b equals to 2, then h can be written as like b minus a by n here. So, that is why we can just write that as like 2 minus 1 by 3 here. So, 1 by 3. So, then we can just use this formula, that as I as 3 by 8 rule for this 3 point, we can just write h by 3h by 8, usually you are just writing. So, 1 by 3, we can just write this one as so directly I can just write this formula, that will be easy to understand. So, 3h by 8 f of x0, that is in the form of like f of 1 here. So, plus 3 f of x1, x1 can be considered as 1 plus 0.3 here. So, we can just consider that one as like 4 by 3 here, plus 3 f of like 5 by 3 plus f of 2. From this you can just obtain all of these values like functional values. Once f of x, if you will just write here in the form of like 1 by 5 plus 3x, from there itself you can just get f of 1, f of 4 by 3, f of 5 by 3 and f of 2, and put these values, and you can just obtain these values here. And if you will just go for the calculation of 6 points here, then repeatedly you have to use all of this 2 sequences, one more sequence you have to add it off to get this final answer here. And if you will just go for this exact value, so the exact value computation is just giving this value as 0.10615, but in 3 point form we are just also getting 0.10616 here. But in like 2 sub intervals, if at a time we are just considering like 6 points, then we are just obtaining this value as 0.10615 here. And this magnitude of error, if you will just compute, so for n equals to 3 we are just getting this value as 0.00001, for n equals to 6. So, this correct value is giving at least up to 5 decimal places here. So, the conclusion is that if we are just using like more number of sub intervals, then this value is just giving the accurate values in both this like exact solution and this like computed solution or numerical solution in the same form. But if you are just considering less number of intervals, then this error is just getting increasing. Thank you for listening this lecture.